So we're back with lecture 6, which is all about elasticity. Elasticity. There we go. So I think just generally we should all be quite comfortable with the concept of elasticity. Things that are elastic, things that stretch to form and then bounce back to some sort of shape. If you think of a bouncy ball, or a hair tie, or bobble, or whatever you call sort of my scrunchies, things that stretch and deform, or react to different things, that when a force is applied they will bend to the force, but they will also have this restorative nature. Springs, elastic strings, all of that sort of thing. So basically what we're going to cover today is sort of an introduction to modelling elastic muscles. Yes. Hello, welcome in. Yeah, so we're going to be looking at modelling elasticity, and we're going to be looking at modelling words are hard today, I've decided. It is a lecture. It's an attempt at a lecture. It's a very chill lecture, so like interrupt and ask questions and do all of that jazz. But yeah, so we're going to be basically modelling elastic things, and then we're going to move on to elastic collisions. So we did inelastic collisions last time when we talked about impulse and momentum. And that assumed that there was always a direct transfer of energy from one to the other. There was only kinetic energy or gravitational potential energy in the system. Now we're going to assume that there's elastic potential energy as well. And we're also going to look at making things more complicated. The goal today is to get to elastic collisions in 2 dimensions, because that's when you start doing some really cool stuff, and the exam questions start looking like things like hitting snooker balls and that sort of things. So if we start with 6.1, as with most things with applied maths, there's just someone else has gone and found the fundamental laws, and we just apply them to different systems. So what assumptions can we make about an object or a body or a particle that allow us to apply certain rules or relationships to it? That's what most mathematical modelling is. So it is perhaps obvious that a rubber band is more elastic than a steel beam. But how is this quantified? Clearly I wrote this when I was feeling very dramatic. There we go. Hook is, as with most of maths, I don't actually know where they're from. Probably mainland Europe. I think that's always... This is clearly a physics lecture. How dare you? As if we would do that here. Actually, I can prove that this is not, because if you look up Hooke's law, depending on whether you're looking at maths resources or physics resources, it's written differently, which I found really interesting. Because, like, it's kind of like saying that British English and American English are the same thing. Yes, they're both English, but they use different rules and, like, phrases to understand each other, but they're both talking the same way and they can understand each other. They just disagree about how things are done. He was English. Classic. Hooke was a Brit. 1635 to 1703, according to Google. You said I found really interesting. I do find it really interesting. You went nerd. Thank you, Cap. Appreciate it. I appreciate you. We all went to Google it. Yeah. I want to know. Anyway, so Hooke, who is a British dude from the 1700s, developed a relationship. Doesn't sound like a mathematician. Which relates natural length, and I'll go into more detail of what all of these things are in a bit. Tension T. Altered length X, and the modulus of elasticity, which we use lambda. So these are all just ways of saying length when undeformed, force present. So remember when we were doing forces and we were talking about things having internal, so like the light inextensible string has some tension. The altered length then is the length when deformed. And I'm being quite careful here because it's the same rule for when things are compressed and stretched if they can be. And this is sort of measure of willingness to stretch. Is it the same thing as Young's modulus? I think so. Modulus of elasticity, elastic modulus, modulus of elasticity, types of elastic modulus. Young's modulus is a type of elastic modulus. Tensile and compressive elasticity, or the tendency of an object to deform along an axis when opposing forces applied along that axis. Yes. According to Wikipedia, yes. So you also have things more broader. So Young's modulus in particular, and the type of elasticity that we're looking at is in one dimension. So when things are affected, if I have sort of a spring and forces are applied, either compressing it inwards or stretching it out, the direction of the force is the same as the direction that the thing moves. In contrast, if I had something and I was trying to shear it, it would be the willingness for... I'm trying to think what would be a really good example here. So shear stresses are things like if I have two things stuck together, say I have like two sheets of paper stuck together and I pull the top one in this direction, its willingness to stretch sort of that way rather than all in or out. So, as an aside, Moduli? Moduluses? Moduludo. What is the plural of modulus? I'm going with moduli. Which is, so shearing is when, like, if I apply a force sort of this way and that way, it's the ability of something to moduli. Okay. Excellent. Yeah, it's the ability of something to sort of get pulled in two different directions and, like, not align with itself. And then you also have something called the bulk modulus, which is volumetric, which is essentially that thing of what happens if it goes out. Something sort of ability to stretch out in all directions. So think like a sponge. Volumetric stress over volumetric strain, inverse of compressibility, extension of Young's modulus to 3 dimensions. Going into shear moduli or like more complicated stresses, get bulk is like pressure. Yeah. So both of those start getting really complicated. Interestingly, shear stresses are something that we think about a lot in fluids, because if you think about near a wall, if you've ever looked at like raindrops that form on, say like you have a glass pane and you have a raindrop that hits and it wants to shape like that, it's going to start doing this. And the reason that it does that is because there's a shear modulus here. One sec, let me go to a different color. There, that is keeping it stuck to the, to the glass. So, but gravity is obviously pulling it this way. So you end up with this sort of, this way is pulling up, that way is pulling down, and you get this shearing stress happening in the fluid. There's fun materials that expand massively to like turn into bike helmet and then compress back down. What is it called? Insulation. If you've ever seen people like spraying insulation and the foams that expand. Or interestingly, hydrogels, which are the thing that I'm working on now. This is my new research area. If you think of things like Orbeez, so those small plastic balls that when you put them in water, they expand evenly in all directions. So I don't know, I've literally just started this project, but there will be things like bulk modulus to consider in that case, because there is a I don't know what you're doing. I assume the liquid would have to be thin layer for modular to use there. Is generally applied to liquid also. So typically with just in the fluid, so like normally for a droplet, yeah, you're right, this is too far away from the wall. So this bit would just be the viscosity, is that measure of how willing the fluid is to shear over itself. So that's viscosity here. But there's a really, really like big field of fluid dynamics that just looks at when you're near a wall, the fluid at that wall isn't going to move. So the bit like right here isn't going to move. It's going to stay attached to the wall. It's called the no slip condition. They're right next to each other. They're not, that force, the friction basically takes over. So the friction overpowers it. And what you end up happening is, if I draw vectors, arrows as velocity, right? You have no velocity there, and then here you have a little bit, and then here you have a bit more, and here you have a bit more, and here you have a bit more, and then suddenly the fluid like starts moving the way it's supposed to. So you end up with this sort of curve of speed. So the closer to the wall you are, the slower the fluid moves. So that is called boundary layer theory. Is no slip condition a set of equations? Yeah, so mathematically you would say that the velocity, no slip, is like u at the wall is equal to 0. Because there's no velocity there. It's not slipping. Fluids is wonderful. We say what things are. There's also the other boundary condition at a wall, which is the no flux condition. There is no flow through the wall. Which has another set of equations. I would love to do a fluid, like, the goal with these streams being completely transparent is to get up to the point where I am confident to give sort of more undergrad level, like fluid dynamics-y type stuff. So if that is something that is interesting, do let me know, because like instantly we're back in my happy place. Have I heard of auxetic materials? I haven't. Materials that can expand when stretched and contract when compressed. Negative Poisson's ratio. Stretch axially, they also elongate transversely. Ooh. This is like sport equipment and stuff is what I'm thinking of. This looks like armor. I want one. It reminds me of those toys that you used to get that like expand, the stars that like expand out and come back in. But yeah, so measures of things stretching, lots and complicated. However, what we're looking at is things stretching or compressing in the same direction. So all that to say that Hooke's law for deformation in 1D is T equals lambda x over L, where, just as a reminder, this is the tension, this is your modulus, so your measure of how stretchy something is, this is deformed length, and this is undeformed length. Okay. If my handwriting is getting too bad, do tell me and I'll slow down. I think that, so the research group that I've just joined is like soft matter and active matter, so more on the hydrogel front in that things when left to their own devices still move and behave, but that's so cool. Wait, this is writing? How dare you? I can... Better? Maybe? I got my doctorate, I had to lose my handwriting. That was how that worked, right? They took it off me. So it is important to note X can be larger or smaller than L. And also, this law only applies to an elastic limit. So that's to say, if you think of like, you know what's a good example of this is like a Mao-am. No, it's not. That doesn't stretch back. A spring. Spring is just the easiest example, right? If you take like a slinky or something, or a spring, and you can stretch it and compress it to a certain amount, if you pull it beyond that, you start losing some of the inherent properties of the spring. It'll start deforming. It'll start changing permanently. For example, the absolute mess that I have. Here's one I made earlier. So I have this slinky that I've done demos with before. And what's interesting about it, beyond that awful noise, I am so sorry, is that it sits like this. Because the demos that I do involve letting 12-year-olds loose on this thing. And what happens is they have bent it so much to the point where it's lost the sort of natural springiness, and now it's permanently deformed. So Hooke's law for like this section versus Hooke's law for this section is going to be different, because this is completely bent out of shape. Still works in terms of the demo, and like, but yeah, these are not very strong, so their desire to, again, sit broken is large. Fun fact. I'm just finding cables everywhere. I have a certain number of springs in my house. Why? Okay. So the other thing to consider whether something is springy, or stringy. And what I mean by that is a spring will be able to be stretched and compressed. But a string, if you think about a piece of string, there's going to be, or a rope, there's going to be some stretch to it, but you can't compress a string, right? If I have a string and I start pushing in on either end, it doesn't hold its shape well enough to like compress down the length of it. It's just going to move out the way. So this one can only be stretched. No compress. So if you were to be sitting in an exam or like setting questions or doing any modeling with this, and you knew something had some elastic potential and you wanted to model it, you have to consider, is it also compressible? Is it possible for the thing to be compressed? Because that's going to change the underlying assumptions that you make on the system. Every switch in my 8 keyboards says tiny little spring in all of them. Huh. Interesting. I thought mechanical keyboards got rid of springs. More you know. Okay. Let's do a units check on Hooke's law. Okay, so remember that the equation is T is lambda x over L. And in particular, what I want to do is I want to figure out what the units of the modulus of elasticity are. So if we look at it, we have, so a tension, which is measured in newtons. So I'm going to do that box thing to be like, this is measured in. Then I'm going to have my lambda, so I'll put a question mark. Now, deformed length is just in, is a length, so it's in meters. And then a length, so that's also measured in meters. So we have something in newtons is equal to something times meters over meters. Well, the meters cancel out. And what we're left with is the units of lambda, units of our modulus of elasticity, is in newtons. So it's a measure in force, i.e. not dimensionless. So if you remember things like the coefficient of friction, those are just scalar values. They don't have any dimension in them. They are just sort of, the bigger the thing, the more force applied, or they are a dimensionless quantity, so we can compare them across. Young's modulus, or in this case the modulus of elasticity, has units. Thinking about the relationship here, then, you have the thing you can get from this, though, is that the larger the deformed length, if you just look at it as a proportional fraction, the larger the x value, the more force is going to be required to get it. So linear relationship scaled by a factor as a fraction of deformation is equal to the tension. They got rid of buckling springs. I didn't know that's how they made those. I remember taking keys off my like old laptop, and then you'd like take the keycap off and a spring would like pop out at you and disappear into the sofa. The compressibility of spring in a key switch can actually affect its field quite a lot. That's quite cool. Well, we could work out how much, if we know the traction thing, and you can work out how much force is needed to apply to the keys. This is an example of that. That's quite cool. I was playing with my, I have a little switch sampler for different keys, and I still don't like the linear ones, is what I decided. I was like, maybe I'll try them. I don't like it. Not those. I thought that would be weird, because they felt quite old. So, with that, let's do actually, I want to do the examples in blue. I think I might start a new trend, a new thing where I do this. Thank you for the follow. Welcome in. Example 1. So we have a spring of natural length 50 centimeters is fixed at one end. The other end hangs vertically downwards and is attached to a weight of 2 kilograms. If lambda is 49 newtons, find the extension. Do all springy materials mostly almost follow Hooke's the linear proportionality mean? To leading order, it's a pretty good example, pretty good approximation. The complicated answer is like no, because typically things have a lot more going on than just a spring. But the way that people get around it is, instead of modeling like something as a spring, they model it as lots of springs. Or they model it as lots of strings tied together. So there's a classic thing in hydrogels is called the Beeden string. I think this is where I get in trouble. Bead spring model. So if you have a big complicated system that does lots of complicated things and in 3 dimensions and everything's happening, they simplify it by just saying that it's loads of springs stuck together with beads, which I love. I love mathematicians. the approximations that we make on life are useful. They're so useful, but they're so stupid. But there are things that are more complicated. So in the same way that like most fluids, if you're going to model them, basically behave with linear viscosity. So they behave in that linear proportionality way. The viscosity, the more force, the more it's going to run, regardless of its resistance. But then that whole field of what's called non-Newtonian fluid dynamics are things that break that. So think like John Tickle running on custard, if you go back to those, or Oobleck, or, you know, this complicated relationship between force and stress. That expands out to the rest of the states, like solids and gases. That's why we did the different spring combination problems in school, the parallel series connections, etc., and combinations of them. Yeah, it's surprisingly very, very relevant. Don't know the things I said. So there's a field of fluid mechanics, or there's a type of fluid that is called non-Newtonian, which essentially says force isn't linear to viscosity, to shearing. So the examples that people go for, if you've ever mixed cornstarch and water, you get this thick sort of runny liquid that behaves, if you move it slowly, so you just like put it in a bowl and you shake it around, it's going to move like a liquid. If you hit it, which sounds insane, but if you hit the liquid or you punch it, it will act like a solid under that force, because the material science, I don't know, I get confused, properties of the fluid basically mean that when a large force is applied, or when a large pressure is applied, it behaves like a solid. That is a many steps away example of something that would break this sort of simple relationship. So there's also the opposite. You can have things that aren't runny, that when you apply a force, they become runnier. So things like ketchup. If you've ever wondered why you shake the bottle with ketchup, part of it is because the oils separate out, but part of it is because it's a non-Newtonian fluid that is thicker when left alone, but if you apply forces to it, it becomes runnier. Fun fact. Don't go around hitting ketchup. It's a weird warning. It's like solid in certain conditions. Yeah, so, and specifically those conditions typically relate to forces. Things change how they behave under force with things like temperature. If you can melt chocolate and it behaves differently. But this relationship of force with stress is precisely, it's that relationship. So most things will behave normally, and then there's like typically the thing that isn't normal is more complicated, or the more complicated version of things. Non-Newtonian fluid videos are great, seeing humans being run on water. I would so... Okay, so if you were watching this stream on Friday and then this morning, I was talking about, like, I've been doing a lot of, like, career thinking. I think I've realised, like, being John Tickle from Brainiac sounds like a vibe. That sounds like a really fun demo that I want to try at some point in my life. But yeah, there are lots of very cool demos out there. I'm like, the smaller ones we could definitely do. But we'll get there. Okay. No, I want color. Try and get in on the bite-sized stuff. I got ghosted from Bite Size. I don't think I've told you that. There's a video of Simon in a leotard somewhere on the web. What the hell? Unacceptable behaviour. Okay, come on. We have important works to be doing, and nowhere near enough time. So, what we're picturing here is you have a string fixed, so normally means to a wall or something, but a point that is not moving. And then vertically down from that, you have a mass. Okay, so when there's a mass pulling it downwards, so gravity is going to be acting downwards, and that means that tension is going to be moving up through the spring, right? It's going to be stretched. We're assuming that there's going to be, well, we're told extension, so we know that there was a natural length here that is 50 centimeters, so we need to convert to metric units, so 0.5 meters, and we're told to find x. So important things to note. Is somewhere in that definition, there should be, metric means SI. Yes, sorry, that's my bad. We should put them in SI units. So the system's at rest. We're assuming it's not sort of bouncing up and down. It hasn't deformed. It's behaving properly. So the force is balance. So that gives T is equals to the gravitational force downwards. So that's mass times gravity. So 2 kilograms times gravity. Then we apply Hooke's law. So we get T is lambda x over L, and we just plug in our values. So we have 2g is lambda, we got told was 49, x over 0.5. So that gives us 2 times 9.8 over 49 times 0.5 is x. So the 2 and the 0.5 cancel out. You got 9.8 divided by 49. So what we end up with, x is 0.2 meters. So the extension on top, I knew there was something I've done differently. So x is the extra length. So I think this is the bit that yeah, so x is distance away from deformed state. So in particular, I should come back here, deformed away from rest state. Delta x is the extension from the natural length. Yeah, so you could write it as delta x. This is where the lots of people writing things in different ways gets frustrating, is because I have seen this law written as kf is minus kx. T is lambda x over L. So there's, I think k is just lambda over L is the answer, but comparing notes, make sure that you know which version you're using is the good advice. 6.2. Elastic energy. So things that we've looked at in previous lectures include things like moments, momentum, impulse, impacts, that sort of thing. Quite often, when looking at things moving, we need to consider energy balances. So that's total energy in a system is conserved. So what types of energy are at play? So previously, when we did energy, work, and power, we said that there was kinetic and gravitational potential. But there's a secret third option. A secret third type of energy. Elastic potential energy. Okay, so that is things like if I take a spring and you can see that its natural length is up high and I compress it down, there is now energy stored in this so that when I let go, it bops up, and I'm trying to do it in a way that demonstrates that like I'm just letting go. I'm removing the force of compression, and then that's happening. Or I can do the opposite and I can pull it apart. Can I do this? I can pull it apart and then let go, and it converts that stored elastic potential energy, right? It's not doing anything, it's not energy yet, it's potential energy, into kinetic energy, and it moves. So when you're considering things that are elastic, you need to also consider their elastic potential energy. That makes sense, actually. We learned that F is minus kx, and we were just told K is newtons over meters because dimensional analysis, fuck you, that's why. If K is minus lambda over L. Yeah, so depending which one you're using depends what your coefficient is and what units you're in and all that sort of stuff. Are springs the common springy things used in practical use, or are there more common ones like we catalogue modulus values for easy use? I don't know, is the honest answer. I live in the realm of theory, so I don't know what would be used in sort of practical things. I think the springs are typically the right, we need to model something theoretically, let's pretend it's all springs, rather than like there just being loads of springs in labs somewhere. Although I do like the idea of that. There's just like physicists everywhere playing with slinkies. That would be fun. So this arises... It would help if I could write properly. Arises from deformation, right? You need to apply work to something to deform it. That stores the elastic energy in that object, and then when it's let go, it bounces back. It then switches from that elastic potential energy into thing. What was the question? What was what question? Is that spring theory? I don't know how far away this is from string theory or spring theory. I don't do physics, unfortunately. Wap wap. Okay, this is the bit where I've decided that I'm going to add in a derivation, so if this is insane, feel free to disregard. So, the equation for elastic potential energy is lambda, we're back to that Young's modulus. How much energy something can store depends on how stretchy it is, over 2L. If you think about it really, really hard, you'll be like, that looks kind of similar to lambda x over L, except I've integrated with respect to x. This is about as far away from string theory as applied English grammar is to complex analysis. You mean the world isn't just made up of lots of springs attached together? It's almost like I don't do physics. So elastic potential energy is the amount of work done in the deformation. So in order to In order to deform something, you apply force to it, you lose some energy into that object, and then it's stored as elastic potential energy. If you would like me to geek out, this is a lot of what goes on with my bouncing droplets. Is there's an energy transfer between the droplet and the bath that deforms the bath then deforms back and pushes back, and that deforms the droplet, and then it... Trampolines. It's all trampolines. Interesting. Well, I'm going to try and do the derivation, so we'll see. To deform a spring from length x1 to x2, so you have to do a certain amount of work to it. Now, when we looked at work previously, I don't think we actually did variable force. I think we only did constant force, but it's the same thing. So when work is force times distance, that is saying that no matter how much work I do, it's always going to be the same amount of force required. Or if force is variable, so if we think of a spring, work is one of those words that is Welsh in my accent. I think that, yeah. Anyway, when the force is variable, if you think of compressing a spring, or you compressing something or squishing something, the more it's compressed, the harder it is to keep going, right? That relationship, it's that relationship between the Young's modulus again and the force required. The more force is required for the harder Young's modulus, so the more compression, it needs more energy. So we say that the work is now the integral of the force with respect to the distance, because the force is changing, okay? And here we're doing it between two random lengths, x1 and x2. So this is for variable work for variable force. Okay. Ooh, don't know what happened there. In the case of a spring, so when a spring has natural length L, x is that deviation away from that natural length. So when it is at its rest state, x is 0. Okay? If I have my spring here, and this is L, x is how far away I move from this. So when I'm at it, I'm at 0. So x equals 0 is precisely L. So what that says is work is the integral to stretch it to some value x, from 0 to x, f of x dx. And to make these values different, I'm going to put a little twiddle there. Bear with. So we know that the force to stretch a spring is Hooke's law, so 0 to x of lambda x twiddle over L dx, twiddle. And then we just integrate with respect to x twiddle. Saying x twiddle a lot is getting weird. So, integrating, we add 1 to the power, divide by the new power. So it's x squared over 2. And then we still have that lambda and L still there. between 0 and x, so we sub those values in. So it's lambda x squared over 2l minus lambda 0 squared over 2l is precisely lambda x squared over 2l. So in this case, the work is precisely, scroll, the elastic potential energy stored. Okay? It's important to note when doing these things that conservation of energy and the work energy principles still apply. Nothing that drastic has happened, it's just energy can now be in a different form, and it is precisely this form. Ta-da! Cheeky bit of calculus for you there. We'll throw in some integration for free. You thought you could get away from it, but you can't. It's always there. Okay. Example 2. This one is a bit more insane. Yeah, let's do it. Okay. So the ends of a light elastic string. So instantly, the 3 things you should be taking away from just that bit of the sentence is string has 0 mass, it's a string, not a spring, and it's elastic. So it's going to change. Of undeformed length 0.4 and modulus of elasticity lambda are attached to 2 fixed points A and B. AB is 0.6 meters. So the distance between A and B is 0.6 meters in that. The tension in the string is T is 8 newtons. A, find lambda. So we have a tension, we need to find the modulus of elasticity. Then the particle is attached to the midpoint particles attached to the midpoint of the string and pulled horizontally in a perpendicular direction to AB at a point 0.4 meters from the midpoint and held at rest. You know it's going to be a good question when it's too long for the board. Held at rest by a force F newtons. B, find F. And C, we'll forget what the start of the question was before we get to it, but we'll get there. Given the particle's mass is 0.3 kilograms, find the speed of P as it crosses AB. Okay, that's a hell of a question, but just to recap, you have the ends of a light elastic string, undeformed length 0.4 meters, and modulus of elasticity, some value lambda, are attached to two fixed points, A and B. So think rubber band pinned down on a board, right? Slightly stretched. You get given the length that it's stretched to, and you're told the tension in the string. Find the modulus of elasticity. That's cool, we've already done that. Then a particle is attached to the midpoint of the string and pulled horizontally in a perpendicular direction. So think, if you've ever done that game where it's a wooden board and there's a hole in it and you have an elastic band and you have to shoot pucks through the hole to the opposite side, it's that sort of shooting motion. I cannot think of an example of what it's called. Like a slingshot, basically. We're talking a 2D slingshot. You're told the force, you're told the mass of the particle. Find the force required to stretch it to a certain distance, and then find what speed it's going to cross back the neutral line with. So let's get going. So first things first, as per always, is drawing diagrams. So we have A, B. We're told that this is 0.6 meters. And we're told that the tension in the string is 8 newtons. So quickly we have, for Hooke's law, I'm going to do the same thing that I normally do with Suvat equations, which is just write out all my variables, see what I'm missing. So T is lambda x over L, which means that we want T, which is 8, lambda, which is what we're looking for, x, which is going to be that 0.6 minus that 0.4, so that's that undeformed length, which is 0.2, and L, which is then the 0.4. Units were all fine, everything was in meters, everything's in newtons, and everything's in kilograms, so we're all good. Okay, we have one unknown and one equation, so let's plug in. Plugging in the values, you get 8 is equals to lambda times 0.2 over 0.4. Lambda is 8 times 0.4 over 0.2, which is 16 newtons. Ta-da! If you ever see anyone doing this as 8 times 0.4 divided by 0.2, don't talk to them anymore. They're not your friend, okay? This is bad. We hate this. This is the clickbaity, ooh, only 2% of people can solve it. They're wrong. They're lying to you. Don't listen to them. Winds me up. Keep seeing them on TikTok and they're like, oh, bear with me, guys. Only give me more money and then I'll tell you the answer. And the answer is it doesn't fucking work. Sorry. Pet peeve of mine. No, what? Are there natural systems with springy energy inside or somewhat approximately, mostly man-made systems? Nuclear energy from atomic scale, naturally occurring things. Ooh, good question. Probably better asked at a physicist. I would say yes. Like, sponge is a natural thing. Grasshoppers store all their energy elastically in their legs before jumping huge distances. Yes, Steve Mould, the mad scientist that he is, made a really cool board. He made a cool board. Made a prop that mimicked the way grasshoppers bend their legs in a really cool way. Lots of naturally occurring materials have a modular staticity and can, up to some threshold tension, deform elastically. For systems where natural materials are naturally held up under tension, you could use climbing plants as an example. Some circubits anchor them. Circubits are the ones that, like, whoop, right? Anchor themselves to other plants using tendrils, which they grow organically into spring-like shapes. Yeah! What Straub said. Generally speaking, though, like animals, plants are good examples. Sponge is a natural thing, right? Like not a plastic sponge, but like a sea sponge. Squish. Also, rubber is a natural thing, but I think we do something to it. Anyway. So that's part A. Part B was we then had this mad deformation thing happening. So we have our AB, but now we have a secret third point. So we now have a new point with a particle, and we're told that this is pulled this way. My thought didn't go into that type of thing, so thanks for the answers. No worries at all. Yeah, on the spot thinking of things is hard. So we have this distance then is 0.6. We have that this distance is 0.4. We're told to find the force required to pull it in that direction. So basically what we're asking is we're looking for Young's modulus, but now in this direction. Obviously we've applied a stretch to it. If you think bow and arrow, beautiful example of this sort of thing. Obviously the bow also deforms, but like bear with me for a second. Like a slingshot, yeah. When we pull it in one direction, shout out to the archery crowd. Though the string is moving, now tension is applied along the string in sort of this direction, right? It's moving downwards because it's pulled along the string. There is sort of a net force and extension happening perpendicular. So we need to be careful, is what I'm trying to say here. So first things first is, let's go back to our system. So we have that lambda is 16 now. We haven't changed the original length of the string. The original length of the string is still 0.4. We don't have this, and we don't have this. So we can find the new length of the string without needing Hooke's law, and then we can use Hooke's law to find the tension and the force. Okay? How are we going to do that, you might ask? It is your boy. Pythag time. Okay? It's just everywhere. Everything is everywhere. If we look at what we had, right? We have two identical triangles. Like this. Where we're told that it's the midpoint. Or we're told that this length is 0.4, and we're told that this right here is the midpoint of 0.6, which means that this is 0.3 and that's 0.4. If you were paying attention last time before, I told you that when you have a triangle that has a right angle, and it's right angle because it's perpendicular, with sides 3, 4, I can tell you without doing any maths whatsoever, that is 5. It's a Pythagorean triple. It's one of those spooky numbers that I don't even need to do the a squared equals b squared plus c squared thing, because I know that that's going to be the case. And you might be saying, Kat, 0.3 is not 3. 0.3 is a tenth of 3. I will tell you that we do the same thing. We scale it all down. So this length here is 0.5. It's nothing that exciting. Samesies. Ta-da! So that gives us that our length of the string is our new length, which is 0.5 times 2. Because remember, it's two triangles put together. It's not just the one. Minus 0.2. So x now is 0.8. Okay. Now we can go back to our Hooke's law, which, just reminder, we're trying to find the tension. We're trying to find lambda is 16 and L is 0.2. So this thing has been stretched quite a lot now. Okay, so we find the tension in the string. So we do please work. Thank you. T is lambda x over L. So T is going to be equals to 16 times 0.8 divided by 0.2, which is going to give us 24. Quick maths. Definitely didn't just look at the answer. However, this is not F. We got told way back here to find F. No F's to be found. But what we've got is the tension in the string. So tension in the string is applied along the string itself. So if we think about the particle, if I'm going to zoom in, right, and I'm a particle P and I have my 2 bits of string coming off it like that, and I have some force here, tension is being applied like this, okay? Because it's the tension within the string. So to find F, we need to figure out what components of that, what's that balance? We know it's held at rest, so we know whatever this sort of net sort of reaction force is, which comes from those two tensions, we need to find it. So we go back to our triangle and we have an angle theta here and an angle theta here. Oh, okay, that's too many things on one diagram. Don't like it. Let's tidy that up. Okay, so this triangle, we said we have this angle here, that's a right angle, that's 3, that's 4, and that's 5. Looking at this diagram, doing our resultant force, we have F equals R, because they balance, and R is going to be 2 lots of T cos sine theta, cos theta. Yes, T cos theta. So that's 2 times 24 times, thank you, cos of theta, which is 4 over 5. Which I did that quickly by using this triangle and using cos of the angle is adjacent over hypotenuse, so 4 over 5. So 2 times 24 times 4 over 5, I believe, is 38.4 newtons. Yeah. Okay. So now we have the force being pulled backwards. So, final part of the question. Let's remind ourselves what it is. Given the particle's mass is 0.3 kilograms, find the speed of P as it crosses AB. So, now we're going to do part C. An energy balance. Okay, so we have some initial EPE. Well, I'm going to say initial is, we're not worrying about that initial stretch. We're just going to worry about, like, it's held at rest. I'm going to draw it, actually. B, P. And that is going to be, so lambda x squared over 2L, held in the string. So lambda is our 16. X here is the 0.8. Two times 0.2. I'm realizing something has gone wrong. That should be 0.6. Earlier on the tension calculation. Yes, so basically what I just twigged was that I said that this was minus 0.2, whereas it should be minus 0.4. I hate having to mark my own homework. So that's 0.6, so that gives us 0.6. So that gives us 48. 16 times 0.4 point. Yeah, 48 newtons. Then over here, 48, which is just a multiplication by 2, which is not too bad. Yeah. So 2 times 48 times 2 times 48 times 4 divided by 5. 76.8 newtons. The worst thing about doing this though, right, is that like I'm trying to get better at posting on YouTube, and then every lecture I make a mistake and I just have to be like, I have to post this now. I hate it. I hate it. I hate it. Okay, so we end up with 0.6. We're back on track. We're back on track. So that gives us all of my answers that I have written down wrong. So we'll do it by hand. 16 times 0.6 squared. 2 times 0.2. So that gives us 14.4. And then our final EPE is going to be when it's sort of at rest again. So here. So this one is going to be 16. Yes. I know where I got the 0.2 from. I got the 0.2 because that was the extension on the previous part. So this is right. Yes, it's still stretched when it's out. Okay, okay, okay. So the natural length of the string is 0.4. So that is 0.4. Oh dear. Thank you so much for the follow. Please support your overtired mathematicians. Natural length of the string is 0.4. This is then, oh. Okay, I did have it right. All good. Now it's stretched out. So the extension from 0.4 to 0.6 is 0.2 squared. Over 2 times 0.4, that doesn't change. This gives us 4 over 5, I hope. It does indeed. It gives us 4 over 5. So we have a difference in values here. What has that been converted into? That has been converted into the kinetic energy in the particle. So we have initial minus final is equals to kinetic energy, right? That's the kinetic energy that's pushed it back. Now we don't know if the string and the particle are touching. We don't know if they've, you know, it's given it enough that it's flung off into the distance. I would assume up to the point where it rebounds, goes flat, they would still be touching. They might not be, who knows. Regardless, that's the kinetic energy that we're going to use. So we have initial minus final, so 36 over 5 minus 4 over 5 is equals to kinetic energy, which from ages ago we should remember is half mv squared. So 36 6. We get 6.4 is equals to 0.5 times, we were told the mass is 0.3 times v squared. So that gives us v squared is 6.4 over 0.5 times 0.3. V squared is, that is an awful recurring digit, so let's leave it alone. 128 over 3. V is equals to the square root of that answer, so 8 root 6 over 3. That seems to be what it says, at the very least. There we go. What I really like about this problem is the fact that this sort of trampolining that is happening here, that slingshot effect, is very similar to what I was studying for my PhD. Like when I was looking at bouncing droplets, and specifically looking at bouncing droplets in 2D, sort of note, I was looking at, you had a particle coming down, hitting something, and then this thing deforming because there's a droplet there, and then bouncing back. And like that force effect, yes, my system was all liquid, but it's the same underlying principle, which is a really cool thing, that like this long question that I've found and then adapted is a sort of A-level exam style question. Like this is something that was probably written by Edexcel or OCR or one of the other exam boards. It's not unreasonable to get sort of a student who's 16 to 18 to solve this problem. This is a lot more complicated, but it's the same fundamental principles. It's just more stuff in it. Is the surface tension there? Yeah, so in my stuff there's surface tension and there's viscosity, and like if these touch it coalesces and dissipates. It's a whole, yeah, there's extra stuff. But the sort of the root mathematics, the bit that I started with was like, okay, well what if this is a solid sphere and this is just a table and it bounces? And then, okay, well what if it's a solid sphere and a liquid bath? And what if it's a, you know, you build it up that way, and that starts from a place of very similar sort of core fundamental bits of modelling assumptions. When it's a sheet in 2D rather than a spring. Yes, if you're assuming that you're working in 2D. If you're just working in one dimension, or you're working in 3D, like you shift up and down. So I assumed everything was 2D, so this would be like an infinite cylinder rather than a ball. But there are more tips and tricks to sort of get around it than I think people realize, which is quite cool, which is pretty funky. The surface of your liquid, yes, yeah. So if you were in like a full 3D system and you had a sphere sort of dropping down here, you would get what is called like geometric spreading, where like obviously the effect of that is going to deform differently to the 2D version. So it is more complicated. It's not too much further away. It did take me, 3 years and a PhD to get, though, so take with grain of salt. Other exact equations related to, do you use numerical methods? I use numerical methods to solve. I don't think there are people working on this area in sort of trying to get exact solutions, but not directly for this specific problem. Yeah. So there. Right, I think I might call the stream there. There is an entire section on elastic collisions that doesn't have a nice stopping point, which is really annoying. And I don't think I can go for another hour and a half. So, this is now going to be a 9-stream series. Whoop whoop. Y'all just can't get rid of me. I'm just going to keep going. I might reassess and break it down into 10 because that's a nicer number. Yeah, that can be done. But yeah, we're gonna wrap it up there. So, in summary, gotta have a summary at the end of the stream. We looked at elasticity. In particular, we looked at Hooke's law and elastic potential energy. One day, I know. We looked at defining what Hooke's law was. We had a nice chat about the fact that different fields will define it differently, so be careful with that. And we had a little detour into what higher dimensional, more complicated versions of measures of elasticity were. And that got me going off on one about fluid dynamics, which is always my favourite time. But in particular, we saw Hooke's law for deformation in 1D. So tension has a relationship with this measure of elasticity, how much something is likely to deform, and the ratio between its new stretched or compressed length and its undeformed state. Which basically told you the further away that something is from its deformed, from its rest state, the more force or tension is stored in it. If you are going to look at something that is being compressed, you need to use a springy type assumption rather than a stringy type assumption. Where strings, you can't compress a rope, but you can compress a spring. So not only is that a tongue twister, it's also a nice distinction between two different problems. We talked about the fact that this modulus is in newtons. However, if you were going to use the alternate form of this equation, it would be in Newton meters. So always really important, whichever sort of base law you're using, to check your units of your fundamental law. So does that balance? Does that make sense as an equation? Is the left-hand side the same as the right-hand side? Because we can't have newtons equals meters. Doesn't make sense. So it's a really good little check to do. We then looked at a little example of a spring holding a mass above a fixed point and trying to find the extension due to the tension in the spring because of the weight attached to it. So nice little example of just taking Hooke's law, figuring out what's missing, plugging all your values in, and getting a result. Then we looked at elastic energy, and we looked at, in particular, elastic potential energy. Talked about how it's treated very similarly to kinetic energy and gravitational potential energy when you have conservation laws still obey, so energy in a system isn't going to change. But in particular, the elastic potential energy is the measure of amount of work done to deform something. And we had a nice little derivation of that where we looked at the force applied for deforming a spring to a certain amount. And we found that the work is exactly the same solution value as the elastic potential energy. Then we had a really long example of a 2D slingshot. So a stretched piece of elastic string being held under tension, pulled back, and then letting a particle go, and try to figure out how fast we could get that particle moving based on its weight. So another nice solve for Hooke's law. Then we did some secret trig, because everything has trig in it. You can't get away from trig. You need to know your trig functions for the rest of your life. Everyone that was like, why do I need Pythagoras? It's everywhere. It's absolutely everywhere. You're never getting away from it. Then I made a mistake, so there's some nice corrections of what I'm doing. So if you are following along or trying to do questions with me at any point in time, by the way, like, call me out. Feel free. I make mistakes. I'm human. I'm fallible. But we ended up deriving a nice equation for the velocity And I talked about how that related to my PhD, because I only finished it last year and I've still got another 3 years of talking about it until everyone gets bored. So that made me happy. Next time we will do elastic collisions in 1D and 2D, and I'm going to go look up a lot of examples of billiard balls, because those are some of my favourite demos for that.